Okay, so we'll start our discussion of probability with a couple of examples. One example will be from an economic study, and the second one will be a COVID example where people were go to emergency and the hospital makes a decision whether or not to test them for COVID. And we can walk through the probabilities associated with that. This first example, it's a study, and what it was, they set up a web page, and I guess they advertised it out. But what they did was they said, okay, you signed up. You come to this web page, you sign up, you choose a question, and that's something that'd be a a life event that you where you want to make a change. So it could be you're thinking about quitting your job, you're thinking of leaving your partner, you're thinking of doing this, doing that. And what they did was they set it up as a game, and what they said was, okay, well, it's heads or tails. So you pick a coin. If it comes up tails, and you pick it right, you have to make the change. So you don't have to make the change, but the toss of the coin is recommending to you that you make the change. So you choose your question. I want to quit my job, and then they go, okay, let's flip a coin. You call it heads or tails. You call it tails, and they flip the coin, and it comes up tails. And based on that, you have to you have to make the change. Or the decision is to make the recommendation is to make the change. And then what they did is they followed up people 2 and 6 months after to see if they took the advice of the coin. Okay, so what were the results? So, okay, the coin, 50-50 flip of the coin. Either the coin recommends that you make the change, or the coin recommends that you do not make the change. And then they followed people up post 6 months to see what had happened. And if I worked my way from the bottom up here, if the coin flip said, make the change, 60% of the people actually made the change. 40% did not make the change. If the flip of the coin said, do not make the change, 60% did not make the change, 40% did make the change. Okay. So if I look at this, so if I have 100 people do this task, 50 of those people, the coin will say make a change. 50 of them, the coin will say do not make a change. And then of those 50 people, of the 50 people where the coin says make the change, 30 of those 50 people will make the change. 20 of those 50 people will not make the change where it makes the change. And of the 50 people where the coin flip says do not make the change, 30 of those people followed the advice of the coin and did not make the change. 20 of those people ignored the advice from the coin and made the change. Now, when I'm looking at this, so of the 100 people, 30% or 30 of 100 people, the coin said make the change, and those people actually made the change. And that's this right here. So if I want to look at what's the probability of a person being in the situation where the coin says make the change and they made the change, what I do is I multiply the probabilities down the decision branch. So the first decision is from the coin. The coin says make the change, do not make the change. Once this decision is made, then there's a second decision. If the coin says make the change, the person either made the change or they did not make the change. For those 50 people where the coin says do not make a change, those people actually made a decision. 60% of those people did not make the change, 40% made the change. If I want the overall probability for each branch, so coin says make change, person makes the change, I multiply the probabilities down the decision path. So 0.5 times by 0.6 is 0.30. So that means if 100 people did this task, 30 people will have had the coin say make the change, and they will have made the change. Now for the coin says do not make the change, the top here, and did not make the change, of 100 people, 30 of those people, or 30%, will follow the advice of the coin and not make the change. How do I figure that out? I multiply the probabilities, or the percentage breakdown, along that decision path. First decision by the coin, do not make the change. Then the person, after 6 months, they follow up and say, well, what decision did they make? Well, if the coin said do not make a change, 60% of those people did not make the change, 40% did. But to figure out overall how many people out of the 100 people that were in the study, I multiply these probabilities along that decision path. So 0.5 times by 0.6 is 0.30. So of 100 people who participated in the study, 30 people, the coin will have said do not make the change, and those 30 people did not make the change. So that's one example of probability. The next example is if we look at the, this is New York City Hospital. So this was between March 1st and April 8th of 2020. So a person shows up in a New York City hospital with COVID-19 symptoms. So they go into emergency. The hospital staff, the first decision that they have to make is, do they test them for COVID or not? So of the people who came in, 11,544 were tested for COVID. 5,914 were released and sent home, suspected of COVID, but they just didn't bother to test them. So they just said, go home, isolate, and if your symptoms get worse, come back. So of those 11,544 people that got the COVID test, 6,265 were excluded or tested negative, right? So they got the test. Of the 11,500 and some, roughly a little over half of them, the test came back negative, or it came back positive, but they had no way of linking it. They had no data. So then that leaves us with the remaining who tested positive. Of those who tested positive, 2,741 were admitted to hospital, 2,534 were not admitted. So when they tested and you came back positive, roughly more than half ended up admitted to hospital. And of those who were admitted to hospital at the time of the study, still in the hospital, no critical illness to date. So that was 12 people. 1,739 completed hospital admission, no critical illness. 999 critical illness. So that 2,741 broke down into 3 outcomes. Still in hospital, no critical illness. Completed hospital admission, no critical illness. And then 990 were critically ill. Now, what does that look like? So this is the same chart as I had before, but I can break that into probabilities, right? So I can say 11,544 adults were tested, 5,279 tested positive, 6,265 tested negative, or they had no positive with no data, whatever that means. So in terms of proportions, 45%, roughly 46% tested positive, 46% tested positive, roughly 54% tested negative. So the next branch down is if they tested positive, what was the outcome? 52% were admitted to hospital, 48% were not admitted. Then you go the further branch down following those who were admitted to hospital. Then 990 had a critical illness. 12 were still in hospital, not critical, and completed hospital admission, no critical illness. And that breakdown here, of these 2,741 people, 999 critical illness, 12 still in hospital, not critical, and 1,739 were completed their hospital admission. Right, so this proportion here, these add up to 100. So I can say of the 2,741, 36% critical, roughly 0.5% still in hospital, and roughly 64% completed their hospital admission. So now if I look at this, I can figure out the probabilities. Whoa. Get my okay. So I can go up here of the roughly. So I tested 11,544 adults. 46% or 0.46 tested positive, 0.54 or 54% tested negative. Of those who tested positive, 48% were not admitted to hospital, 52% were admitted. Of those admitted, 63% completed the hospital admission, 0.4%, less than 1%, were still in hospital non-critical, and 36% were critically ill. And I can figure out, so I've got, what do I have? I have 11,000 people tested. I can figure out what's the of the 11,544, what's the probability of a person being admitted to hospital under critical care? Right? So that would be of 11,554. So if you show up at the hospital to get tested, you're sick with thinking COVID, and you get tested, what's the probability that you're going to end up in critical care in ICU? And how I do that is I multiply the probabilities along the path. So if I take what this would be is, it would equal 0.4573 times by 0.5192 times by 0.3612. So that I multiply the proportions or the percentages down the decision branch or the outcome branch, tested, outcome positive, outcome admitted, outcome critical illness. If I multiply those probabilities down that path, that'll tell me if you show up at a New York City hospital during that time period, if you showed up to get tested and and they said you should get tested for COVID, the probability of you ending up in ICU and in critical care is that value. And that value is there was an 8.6% chance that you would end up in critical care. So roughly 8 of those who showed up at the hospital and they decided they should be tested, roughly 8.6% of those people ended up in the hospital with a critical illness. And that's these values here. So here are the probabilities of each possible outcome. Right, you test negative. That's 54% of the people tested negative and then we're just, they're gone. 22% tested positive, but were not admitted to the hospital. Of those who were tested, 15% were admitted, but they ended up being released. Less than 1% or 0.1% were admitted but still in hospital. And of all those people tested, 8.6% of them ended up in hospital and critical care. And that's where that 0.857 comes from. You multiply the proportions down the decision, in this case, the outcome path. And I can see This is an exhaustive list of all possible outcomes, and each outcome is mutually exclusive from the other. So you come in, you test positive, you test negative. Of those negatives, nothing more is done. They're gone. They've left the hospital. Of those who test positive, 22% are not admitted to the hospital, and that outcome, they're done. They're not part of the hospital care anymore. Of those who tested positive and were admitted to hospital, there were 3 outcomes for them. They completed their admission, and they were gone, so they survived and they were, I guess, healthy. Less than 1% of them, so 15% of them, that was the outcome. You went in, you got checked into the hospital, and you were gone. Less than 1% of them were still in the hospital at the time, the study, but not in critical care. Oh, this one here is critical illness. So, critical illness. And that ended up with a critical illness in ICU was 8.6%. So that's an example of how we can use probability and proportions or percentages to determine for a base number of people, in this case, number of people tested for COVID. For the coin toss study, the number of people who participated in the study. And what we'll do next is we'll just do a more theoretical explanation of probability.